this video, we will be talking about hydrogenation of alkenes. It's yet another addition reaction. It's a very simple one in that the two groups that you add to the double bond are both hydrogens, and so we don't have to worry about which group gets which thing. It's very much like diol formation, which was the previous video, in that it was also two groups being added that are the same as each other, and it was a syn addition, as this one is too. Both hydrogens add on the same face of the double bond, so there's the double bond. Both groups add to the top or to the bottom. Before you continue, you probably should read the introduction to section 6.6 on page 235. It's a very short section. Now, this reaction, as I've shown, is the main idea. I showed the product twice because you can either show the hydrogens explicitly or because these, at least in the stick figures, the fact that these are drawn with 3 bonds to them suggests that there's a hydrogen at each of those carbons. The reagent that we use is just hydrogen gas, so just H2. It's the simplest molecule there is. One hydrogen adds to one carbon, the other hydrogen adds to the other carbon. Very simple. But it doesn't just happen by itself. It's a very slow reaction unless you add a catalyst. There are a variety of different catalysts that can be used. Literally hundreds of them have been developed. The simplest ones are certain metals, like, for example, nickel, platinum, palladium. Those are the most common ones. There are many others as well. So let's look at the first reagent, which is just hydrogen gas. I've shown a picture of a hydrogen gas cylinder here. You attach the cylinder to your reaction vessel. And this is a picture of what's called a bar hydrogenator. So you put your sample in here. You attach the hydrogen on here. You can control the pressure of the hydrogen that's going to be in contact with the reagents inside the cylinder. And this is just a machine that actually shakes the sample. So you move it around and it makes the reaction happen. So you're going to add your alkene, your catalyst, and some sort of a solvent typically into here. So what about the catalyst? Well, as I've said, it can be nickel, palladium, platinum is sometimes used. This is a symbol for palladium on charcoal, which is a way of putting in the catalyst in such a way that it's very easy to recover. Palladium and platinum in particular are pretty expensive, so you want to recover the catalyst so you can use it again another time. As I said, there are many others. There are even some organic compounds that can serve as hydrogenation catalysts. Here are some examples. So take this alkene, add 2 hydrogens to the double bond, becomes a single bond. That carbon that didn't have any hydrogens to begin with now has 1. That carbon that had 1 hydrogen to begin with now has 2. And the product is always what kind of compound? Just an alkane, unless there's some other functional group in somewhere else in the molecule, which would still be there. Some functional groups, other functional groups may be affected by hydrogen, some may not. Okay, here's another example. Simple alkene, this time is drawn as a stick figure. Again, when you add hydrogen, it just adds across the double bond, and the double bond becomes a single bond. And the beauty of a stick figure is you don't even have to show anything else, just show the double bond becoming a single bond, and that implies then that that carbon that had 1 hydrogen now has 2. That carbon that had 2 hydrogens now has 3. It becomes a methyl group. Here's another example, this time on a ring, and that shows the stereospecificity in particular. So when you add 2 hydrogens across these 2 carbons, it becomes a single bond. But these 2 methyl groups that were on the double bond now end up being cis to each other because the 2 hydrogens that added in add to the same side, and that means the methyl groups have to go to the same side. So if the hydrogens added to the top, the methyl groups would go to the bottom. If the hydrogens added to the bottom, the methyl groups would go to the top. Now in this particular case, notice that we don't have to say plus enantiomer because this is not a chiral compound, it's a meso compound. It has a plane of symmetry right through here, so the structure with both methyls down would be the same as the structure with both methyls up. Just by comparison, notice that this carbon is chiral, and that's because it has a methyl, a hydrogen, an ethyl, and a propyl group, so 4 different groups on this carbon. It's chiral. The starting material in this case is not chiral, and so what the rule says is if you create a chiral molecule from one that was not chiral, you have to get both enantiomers. So should we put plus enantiomer in this case? And the answer is no, because this kind of structure, since it doesn't actually show the stereochemistry, implies that both enantiomers are there. Notice in this case, that carbon is already chiral, and so if this were the R enantiomer, it would still be R in this case. If this were S to begin with, it would still be S in this case. So again, we don't have to say whether we get both enantiomers or just one or the other enantiomer because we don't know whether that carbon is R or S or both. And so whatever it was to begin with, that's what it is in the end. In other words, that carbon is not affected by the reaction at all. So So here are some more examples. I want you to go ahead and stop the video and see if you can write out the products for these reactions. The first two are very simple, and I won't go into those in more detail. You can ask about them in class. This one is a little more complicated, though, because of the stereo specificity. Remember, because it's in a ring, that methyl group, when it's on the double bond, is in the plane of the double bond, so it's not shown as a wedge or dotted line. But this one is not on the double bond, so it is shown as being up. That's why it's drawn with a heavy line like that. So what's going to happen when we add hydrogen here? Well, think about this, and I'll let you draw the structures of the products. There's actually going to be two products. If the hydrogens come in on the top, they will both add to these carbons, one on the top of this carbon and one on the top of that carbon. That would force the methyl group to go down. It would then be trans to this. On the other hand, if the hydrogens add on the bottom, that's going to force the methyl group to go up, so it's going to be cis to this. So you get one product that's cis and one product that's trans, and those are actually distereomers of each other, and so you would get both, not necessarily in equal amounts, and you can think about which one you think you would get more of. And we can talk about that in class. Thank you for your attention.